On the different matrix systems that are typically used in composite systems. Um, I realize that this lecture is a kind of a mishmash of different things, but I'm trying to. I had put this together, so I'm just following the slides just to explain what the information is all about. So, talking about um, one of the most important matrix systems that is used in polymer composites are epoxies. It is the second most widely used resins for composites after polyesters, but it is the most used resin system for engineering applications, especially high-end applications, because it is neither um, as expensive as some of the most exotic resin systems, but it is not as cheap as polyester and similar resin systems. But what you will also find is that there are many applications that are not exactly for composites. They are for non-reinforced type, such as for coatings and adhesives, or if you have a laminated sheet, or if you had circuit boards or something that needs very high dielectric strength, low off gassing, etc. But of course, not all epoxies are good for, say, something like a space application and things like that. They have reasonably good thermal stability, very good mechanical properties, so they are used quite extensively in advanced composite materials. So, what is a typical epoxy structure? It has a three-ring epoxy group, or it is sometimes called the oxirane group or epoxide group. And the cross-linking occurs right here, where it can be directly attached to another organic group, or the R, or the common group. It could be a simple one or a complex one. So depending upon how complex it is, you can get the right kind of properties. And another carbon plus epoxy ring combination is called the glycidyl group. So in some ways it is very similar to a carbon-carbon double bond in unsaturated polyesters, but you may also find epoxy ring or epoxide groups, which is less frequent compared to carbon-carbon double bonds. Just to give you an example of how these epoxies are formulated, several methods are used. You are adding an epoxy ring to the end of a polymer chain or creating a polymer containing the epoxy rings. And it is done by the epoxy manufacturer. So depending upon the kind of polymer that they select, there are different kinds of resin systems. And but this part of the synthesis is not part of the curing or molding operation. And the typical epoxy reaction is given below. I don't want you to go too much into depth of this, but just understand that this synthesis is done outside of the curing reaction. So you are starting with the what is called the bisphenol A and epichlorohydrin, which is a highly reactive monomer. So you have an ether linkage and bisphenol A. So depending upon that, you get different combinations. And in this case, it is called diglycidyl ether bisphenol A, or the acronym is called DGEBPA. This synthesis reaction, as I mentioned, is done in very large chemical plants. The cross-linking reactions by themselves are conducted or created during the molding operation, where you are adding OH groups to the molecule, which is formed as part of the curing process by a curing agent. And these curing agents are amines, so that can add the OH group to the molecule. The hydroxyl groups is the one that provides the addition to the final cured polymer. So there is some uh, water and things like that that are released during this reaction. So you the there are several OH groups in the epoxy and non-epoxy ring portion, and the properties of the products depends upon the number of um, number of bisphenol A units. So if you had two, then the heat distortion temperature would be about 105. So if you have more number of units, then the heat distortion temperature goes up. So which means that by selecting the right kind of epoxy, you can get the right kind of heat distortion temperature. There are other epoxy types where you can have more crosslinks with more functional groups, so the properties will change accordingly. So, what are the common types of epoxy molecules? You have just aliphatic chains. You could have an aliphatic which is a cyclical chain, or you could have an aromatic straight chain or an aromatic cyclical chain. And these structures vary in thermal stability. And higher the aromatic content, higher the heat distortion temperature. And the other thing to note is that cyclical polymers are better than straight chain polymers. Here are some more epoxy types. Anyway, just know that there are many, many different kinds. There could also be epoxies with halogen additions such as chlorine and bromine, which are used where you need fire resistance. So you may have some conditions where you have epoxies with chlorine and bromine, but they are not always they have great properties. They don't catch fire that easily. What you need to know is that the fire resistance of a polymer is not based on how fast it can catch fire. It is based on how much of char is created. So the more char is created, the less chances for that fire to continue further. But if you had additions such as chlorine and bromine, what happens is that they would dissociate from the ring and combine with hydrogen atoms to form hydrogen bromide or hydrogen chloride that will smother the fire, but unfortunately that gas is choking and it is irritating to the eyes and mucous membranes. So good in the property but bad for health, and it can be hazardous or toxic. There are also epoxy resins with high thermal resistance, and in this case there is an imide based polymer that is used as a basis for the epoxy resin. I realize that all these chemical terminologies are not going to be that evident to you, and it won't come naturally to you, but just know that there are epoxies and there are different kinds of epoxies and they have different kinds of properties. Straight chain has less properties compared to cyclical chains. uh, Aliphatics have less properties compared to aromatic chains. So that's all you need to know. Imide group is stiff and stable and increases thermal stability. So when you have epoxies, it is not always the best material for toughness. So if you have a composite material with an epoxy matrix, they may not always be tough. So you have to know how to add toughness to the matrix. So in order to do that, you have to make the polymer chain more flexible. So you can add aromatic content and add linear aliphatic segments. Or what you do is you add rubber polymers between, or you add rubber particles, or you add what are called thermoplastic polymers to the resin system. So that gives some kind of a flexibility and plasticity to the matrix. Coming to the actual reaction itself, the epoxy group is where the cross-linking occurs in epoxy resins. And it is usually at the ends of the polymer chain, or in some cases, it is at the end of the side chain. It is never in the middle of the chain because the epoxy ring only has one attachment point. If the second attachment is attempted, then that ring will open and it will destroy the properties of the epoxy. This is what typically happens when you have oxidization reactions or when you have reaction with moisture and things like that. So it cleaves the bond, the epoxy bond, and reduces the properties of the matrix itself. When you have active sites on the polymer, um, they are present along the backbone of the polymer in each of the polymer repeat units. And one thing to note is that because the epoxy group is at the end of the chain, you have much greater choice in the nature of the backbone for epoxies than for polyesters. So epoxies have got greater flexibility for the types of reactions that can take place compared to polyesters. So the cross-linking is what typically happens in the curing reaction. It is based on opening up of the epoxy ring by a reactive group, and that reactive group is part of another molecule called the hardener, and they typically have amine groups or ammonia groups at both its ends. And what happens is that the hardener will react with two epoxy groups on two different molecules, and they will just link together like hand holding. So they will hand hold very strongly, so it will be very difficult for you to pull them apart. So what happens is that once this reaction takes place, it is not reversible. So which is why a thermoset reaction in epoxy is non-reversible. So you cannot go back to the monomer and form the reaction all over again, just like in the case of thermoplastics. So these are the amine groups, and this is the epoxy group itself. So this will now react with the epoxy ends and chain them together. And sometimes what you will also find is that if this is a complex molecule, then this will have directionality. So which means that the whole thing is there are more directional bonds which will contribute to the improvement of the strength. So a straight chain will have less mechanical properties compared to a complex chain. just understand that the amine group will just bond with the carbon and break open the uh, nitrogen bond, and it will form the carbon bond. The hydrogen, which is slightly positive, will then bond to the oxygen that was part of the epoxy ring. So this carbon nitrogen bond is a critical bond for cross-linking. It is not the same as the free radical cross-linking reaction used to cross-link unsaturated polyesters, or things that are much simpler reactions. And the epoxy reaction will also create an OH group that is important to some of the properties of the epoxy resin itself. So this is the ring opening reaction, and then it just bonds that together to form the final bond. So this is more chemistry. Don't worry too much about it, but just understand that there is a cross-linking taking place between the carbon double bonds and the nitrogen double bonds in the hardener. That's it. The epoxy cure reaction does not always result in a byproduct. And so the advantage is that most of the time the amount of shrinkage that happens as a result of the curing reaction is very minimal, unlike in the case of a phenolic cure reaction. In the case of phenolic cure reaction, you are probably going to have about 10 to 15% reduction in volume, whereas in the case of epoxies, you might maximum have 1 to 2% reduction in volume, maximum. So you do not have to worry about the byproducts of the cure reaction. And it is different from byproducts formed during synthesis reactions. Sorry, this is a lot of information here. Again, it's just there to give you that information, that's all. Now, there are many different kinds of hardeners, and it will have different kinds of groups that will open the epoxy ring: amines, amides, acids, phenols, etc., etc. So most common one is the amine one. And in almost every, in every case, the reaction is started merely by mixing the epoxy with the hardener. And when the active site on the polymer comes into proximity with the epoxy ring, it will uh, it will start reacting. And in order to facilitate that reaction, you heat up the reaction, which is part of the curing reaction. And heating may also be required to activate the reaction of some hardeners. So the epoxy and hardener are often referred to as part A and part B. So most of the all the epoxies are two-part epoxies. They have a they have the epoxy and the hardener. Okay, so they are two-part. So you generally euphemistically call them two-part epoxies. So there are many different types of hardeners, and depending upon the groups that are there present, you have different different hardeners available in the market. So what kind of density do you require? What kind of ratio of hardener to epoxy do you require? And most of the time it is based on the stoichiometric ratio of active sites of both epoxy and hardener, and the molecular weight of both epoxy and hardener. So if you use the right kind of stoichiometric stoichiometric ratio, then you have the maximum cross-link density. And you know that higher the cross-link density, the stronger the material or the stronger the matrix, and less susceptible to attack by solvents, etc. But the stronger it is, the lower the toughness. So you do not want to add too much hardness. So just because you want the reaction to take place faster or better doesn't mean that you should just add a whole bunch of epoxy. So when you create the epoxy reaction, you want to add the exact amount. Sometimes even one extra single drop of additional hardener is bad. I mean, it can create some kind of a it can even create a slowing down of the reaction because there is too much hardener. So you want to add the exact amount. Now, there are some precautions that you need to take for those people who are actually on the shop floor and handling these chemicals, because some of these uncured reactants are toxic. They could, at the very minimum, they have been known to cause skin irritation. So you have to use plastic or rubber gloves, the right kind of gloves. And the other thing to note is that most of the epoxies and hardeners have low vapor pressures. So you have to use some kind of a respirator to prevent the inhalation of those fumes. So this one gives you on a single table comparison of properties of epoxies and polyesters. So you can see that more the epoxy, better. But the thing to note, especially on the shop, on an industrial level, is that epoxies are moderate expense, whereas unsaturated polyesters are low. So if you buy it from, say, a standard supplier such as fiberglass or something like that, their common epoxies that they sell, the maximum volume is of the order of about I think for per gallon is something like $10 to $15 or something. Not even 10, I think less than $10 per gallon. Or there could be, a 5-gallon drum for some of the better ones is like, $500, $575 or something like that. That is what comes to my mind. So I would like you to do a simple homework assignment, and I want you to look at some of the standard epoxy resins. These are some of the common ones. 977-3, which is the aerospace grade. 8552 is also an aerospace grade, but it is less expensive compared to 977-3. Then you have EPON 828, EPON 865, and I would like you to compare properties and costs. So there are some specialty resins like cyanate esters, phenolics, BMIs, polyimides, etc. So the more specialized they are, the more expensive they are, and the harder it is to process. So especially BMI, they have very high temperature. You also have very high curing temperature, like the processing temperature is like 450 degrees centigrade, and at room temperature it is solid, so you have to heat it up in order to even infuse it or add it into the matrix, into the fiber reinforcement itself. So you could also use them in pre-preg form and things like that, where they have already been included into the fabric or the fiber, and it is much easier to use them. So these are some of the standard ones, and this one shows you the some of the commercially available BMI resins. The most common one is SciTech 5250-4, and especially for high temperature applications like for rocket nozzles or for cowling ends and things like that. I think some of the common examples I know are, I mean, there is a lot of BMI use in the F-35s and things like that. Okay, so anyway, I'm going to stop here. I mean, this is the end of the lecture 3, and we will continue in the next set of slides, next set of lectures.